Fusion energy has been gathering a lot of attention lately as researchers try to stabilize and maintain consistent and efficient fusion reactions right here on Earth. But what is fusion exactly? How does it produce energy? And why is it so difficult to achieve outside of a star? When we fuse two particles together, we expect the end product to have two particles worth of mass and energy within. A proton has a mass of 938 megaelectron-volts, and a neutron 940. If we were to combine these together to form deuterium, we would expect a mass of 1878. But in reality, deuterium's mass is 1876 megaelectron-volts. Something's missing. This drop in mass is attributed to the strong nuclear force. How's that work? The strong nuclear force and the strong force are actually two different mechanisms. They are both mediated by the strong force, but the gluons that hold quarks together are not what hold nucleons together. The strong nuclear force is quite complicated. It's a byproduct of the force holding nucleons together. I will do my best to visualize and explain it. The three main or valence quarks inside a nucleon possess a charge. But unlike the standard positive or negative binary charges we are used to, they have three charges or colors: red, blue, and green. The term colors is used because if you mix the three together, you get a neutrally charged white. Don't let the colors aspect confuse. They could have named the charges any arbitrary name. But the mixing of colors is fairly intuitive, so we call these charges colors. These three quarks are in a state of superposition, with each one constantly changing colors with the others. This is accomplished by emitting virtual particles we call gluons. Gluons contain two charges, a color and an anticolor. The color of the gluon will be the color of the emitting quark. The anticolor will be the anticolor of whatever the emitting quark turns into. So, for example, if a red charged quark emits a gluon and turns into a blue charged quark, then the gluon will have the color charge red and the anticolor charge anti-blue. This gluon then is passed to the blue quark, where the anti-blue cancels out the blue charge and the remaining red charge is passed off, creating a red quark. Sometimes, if an emitted gluon has enough potential energy, it can split and become a quark and antiquark pair. Now we have 5 valence quarks in our nucleon, which is not impossible. The only rule is that whatever our system is, it needs to be color balanced. But this is a less stable energy state than 3 quarks, so two things can happen. Either the quark-antiquark pair can annihilate each other back into a gluon, or we can swap out our quarks to create 2 color balanced systems. When our system is composed of an odd number of quarks, it's called a baryon. When it is composed of an even number, a meson. This meson is called a pion. What does this have to do with the strong nuclear force? If two nucleons or baryons get close enough to each other, then the produced pions can interact with the quarks of the other nucleon. Let's look at an example. A green up quark in our proton emits a gluon that splits into a quark-antiquark pair with the gluon's respective colors. The original 3 valence quarks are now color imbalanced. The newly formed green quark replaces the newly formed red quark, establishing color balance, and our pion leaves the proton. The pion then interacts with the quarks in a neighboring neutron. The antiquark will annihilate one of these quarks, producing a gluon, which will then change one of the other quarks, maintaining color balance as the other quark joins the neutron. This is a neutral pion interaction. Let's imagine the exact same scenario, except this time the gluon splits into 2 down quarks. Now when we swap quarks, we have 2 down quarks in our baryon. This means our proton has become a neutron. Our pion is now a positive pion, and when it reaches the neighboring neutron, the annihilated down quark is replaced by an up quark. Positive pions create protons out of neutrons, and the inverse occurs with negative pions. During fusion, these pion interactions fundamentally alter the wave functions of the 2 nucleons. They are no longer 2 single entities. We now have a wave that interacts with its surroundings as a single quasi-particle. But why does this new quasi-particle possess less energy or mass? The quarks in a nucleon are confined within a small volume by the strong force. This is known as containment. The force and energy to keep quarks contained increases linearly with distance. If the distance becomes too great, the amount of energy produced stimulates the production of a quark-antiquark pair, which then cuts the distance in half. This is how pions are formed. Because of containment, there is no way for gluons to attract things outside of this volume. Pions can break containment and exit the volume of our proton before they decay. These exiting and decaying pions contribute to the long-range structure of the nucleon. Or that is to say, they determine the distance at which the strong nuclear force can exist. The wavelength, or probability of the pion particle's location, is proportional to this radius, and wavelength is of course proportional to mass. When two nucleons are brought closer together, the probability of a pion particle tunneling and interacting with the other nucleon increases. This interaction is coupled with a subsequent increase in the radius of localization. What does this mean in simple words? Normally, pions are only found in this volume. Since particles are waves, those wave functions need to fit in the volume. When two nucleons are brought together, the pion now has a larger volume it can occupy. In quantum mechanics, whenever you increase the volume in which a particle is confined, it will often decrease its momentum or increase its wavelength to reach a lower energy state. Now that we have a larger volume that the pion can exist in, its wavelength increases, and since wavelengths are proportional to mass, their masses decrease. This is where mass defect comes from, and it's why fusion produces energy. The next question is, where does this energy that is created from fusion go? You may have heard that momentum, much like energy, is conserved. Momentum is simply mass times velocity. So if the mass of our fused particles drops, then the momentum also drops. Therefore, we need to pass off the extra momentum to somewhere else. When deuterium and hydrogen fuse, that momentum is passed off into a photon. When deuterium and helium-3 fuse, that momentum is directly released as the kinetic motion of the resulting products. These then smash into other particles which can help them achieve fusion. Don't forget, kinetic energy contributes directly to heat. So when you hear people say fusion produces heat, this means the particles are now moving faster afterwards. The last question to answer is, why is fusion so difficult on Earth? Protons are of course positively charged. They repel each other with tremendous electrostatic force. The protons in a helium nucleus repel each other with a force of about 25 newtons. This is an absolutely insane amount of force at this scale. If you were to linearly scale up the distances and forces, then two marbles held 3 centimeters apart would repel each other with a force of 250 trillion newtons, or the weight of a sphere of iron with a radius of about 1800 meters. The only way for protons to overcome this extreme repulsion is to slam into each other with extreme speed and kinetic energy, roughly a quarter of a mega electron volt or 2% the speed of light. This would equate to a temperature of about 3 billion Kelvin. We can cut this temperature in half, so fusion will occur when two protons collide head-on. This would still be excessive to maintain a fusion reaction, but that 1.5 billion is 2 magnitudes larger than the temperature found in the Sun's core. Our Sun, like most stars, isn't big enough to achieve the temperatures necessary to maintain fusion. They shouldn't exist, and by extension, neither should we. Thankfully, we have quantum mechanics to thank in the form of quantum tunneling. In our world, a barrier is a barrier. It doesn't really make sense how one could just pass through a wall. But barriers like these don't really exist in the quantum world. The universe is empty space and fields within that empty space. When our protons approach each other, there is no tangible barrier preventing them from doing so. Simply, the electromagnetic field dampens the probability of this occurring. The quantum world is probabilistic in nature. We talk about particles and I show you little spheres, but in reality it's density functions representing the likely location of the excitation in that field we call a particle. The larger this wave's amplitude, the more likely it is that the thing we call a particle is in that location. During quantum tunneling, this wave approaches our quantum barrier. It could be the electrostatic repulsion of the electrons in a wall, or the Coulomb barrier of another proton. As our wave approaches, the portion moving towards the other proton starts exponentially shrinking, while another part starts moving away. It looks like our